I welcome you to the second lecture, Some Basics. In this lecture I want to summarize key features of the structure of the Earth, linked to the global climate system. So in part A I will talk about the structure of the Earth. Okay, we're talking about different spheres, starting from the lithosphere, then talking about the atmosphere, the ocean, and then the ice system, the cryosphere, and just feature some of the key the highlights. Okay, lithosphere, for example, that's where we get our fossil fuels from. Okay, lithosphere is also linked to the drift of tectonic plates, continental drift. It also creates earthquakes and volcanoes. Okay, atmosphere, I introduce you to composition and structure, and indeed greenhouse gases will be featured, and other things. We're talking about the ocean, composition and structure, and the ocean. There's a direct link actually to the formation of sea ice. Okay, and you learn a little bit about that. Okay, in part B, I just want to talk about key scientific processes, so that you learn the names and learn a little bit more about these processes, like thermal radiation, like transmission, absorption, and reflection, like phase changes of water, like rainfall, precipitation, or evaporation, that you learn these words. Okay, and in part C, we focus on the understanding of key scientific terms. So what are cycles? What are fluxes? What are budgets? What are anomalies? And this is really, really important, because there's climate, in the climate sciences we regularly hear about anomalies, temperature anomalies, wind anomalies, water budgets, water fluxes, solar flux, water cycles, carbon cycles. And you need to understand these terms. Okay, so let's talk about the structure of the Earth. Not the entire Earth, we only talk about the lithosphere first. Okay? All right, lithosphere. There's a little sketch above me of the lithosphere, and we're talking about the rigid outermost rocky shell of Earth. Okay? We have continents, and we have oceanic crusts, that's the seafloor. Okay, so the lithosphere is composed of the continental and oceanic crusts and a portion of the upper mantle, subdivided horizontally into tectonic plates, and the movement of individual plates causes earthquakes and volcanoes. And volcanoes are linked to the climate system. Okay? The lithosphere also contains oil, natural gas, and coal reserves exploited by humans as fossil fuels. That's a big feature of the lithosphere. It's the fossil fuels that we use to create electricity. Okay, so oil, natural gas, and coal formed from decomposed organic matter, typically from ancient marine microorganisms on continental shelves or plants in swampy wetlands, deposited over the past 550 million years. It took a long time to form these deposits. Okay. All right, so now we come to a little intermission structure. It looks like an ad, but it's not an ad. Just want to introduce you to the fossil fuel lobby. Okay, featuring the Seven Sisters. You can see who that is above. Seven Sisters are major oil companies. Okay, so what is the fossil fuel lobby? It's paid representatives of large fossil fuel companies and electric utilities corporations who attempt to influence governmental policy. Okay? And what are they doing? They sponsor certain political parties and politicians in order to preserve their own economic growth. They try to discredit the scientific consensus of global warming. They try to sabotage global incentives such as climate conferences. They continue to invest in alternative technologies involving fossil fuel like clean coal, gas fracking, shale gas extraction, etc. Okay, so we're coming now back to the main storyline of lithospheres and the plate tectonics. The friction between adjacent plates creates volcanoes. And this one shows you a list of active volcanoes, all these red dots, and you can see that it happens where the neighboring seafloor plates create friction. Okay, and featured here is the Ring of Fire in the North Pacific Ocean. Okay, you see the Ring of Fire featured all around here. So what's the link of volcanoes to climate, to the climate? Well, volcanoes emit greenhouse gases and aerosols, and both can influence the climate. Okay, the greenhouse gases more on the longer term, and the aerosols more on shorter terms. And you learn about that in the future, but it's linked to plate tectonics, the movement of plates. Okay. All right. So now, next one. Still the lithosphere. Why is it also important to know about the continental drift of tectonic plates? Well, it's about the reconstruction of past climate change. Okay? And you know that on Earth we have different climatic zones. You know that it's near the equator, it's warm and humid. Okay, then we have regions which are still warm but relatively dry, and we have very cold regions, the polar regions. So now if you take a sediment sample and you want to know what was the temperature 200 million years ago, or 20 million years ago, whatever time, you need to know where that location was positioned relative to the equator or to the geographical latitudes on Earth. Okay, and here's the history of how the continents look like. And you can see the original initial configuration of Pangaea 225 million years ago. You can see the equator and the different continents clustered in one large composition. Okay, and then breaking up and creating Gondwana and Laurasia at that point, and then up to now where we have the current configuration. Okay, so how does it influence climate? Okay, it influences climate also because it modifies the ocean circulation. Okay, so it matters when that, in terms of longer million-year type of climate changes, it matters whether you have a current that runs around Antarctica, the so-called Antarctic circumpolar current, or not. Okay, so it determines, as I said before, the positioning of a region on Earth. Okay, and it also informed Darwin's theory of evolution. So you can imagine that in past climates, if regions were close together and in a particular climatic zone, that similar plants and animals formed. Okay, and then separating these regions explains where some region on both sides of oceans are actually similar. Okay, and you can follow a little bit through if you look, if you a little bit explore which regions were actually close together, you can see that South America and Africa were very close together in some, 150 million years ago. So, all right, anyway, let's go on. Let's talk about the atmosphere. We're talking about air. Okay, what's in the air? Okay, let's talk about the composition of the atmosphere. Okay, and we have a table here, and the table lists permanent gases and variable gases. Permanent gases are gases where the contribution does not change much. Okay, and permanent gases, the key ones are nitrogen and oxygen. Okay, nitrogen 78%, oxygen 21%. And you know where the oxygen comes from. It's created through photosynthesis. Okay, and it's created through the conversion of carbon, essentially, and the solar energy into oxygen and sugars. Okay, that's a very, very important. That's why we're here. Okay, that's one reason why we can live on Earth. Okay, but let's look a little bit at the other contributions. Okay, the other contribution. Water vapor plays a super big role because water vapor is the dominant greenhouse gas. Okay, and you have a percentage of 0 to 4% of air is water vapor. So that creates the humidity in the air. And that's the link. It's an extremely important component in the water cycle. It's what creates clouds, what creates precipitation and stuff like that. But without water, without the greenhouse gas effect, and you will learn about that greenhouse gas effect in the future lectures, Earth would be some 15 degrees cooler. So it would not be possible to live on Earth. It's because of the greenhouse effect. So now there are other greenhouse gases which have a relatively low percentage. Okay, very, very small concentrations. Carbon dioxide is the next biggest one. Okay, percent by volume is way less than 0.1%, but you can express it in parts per million. 380 parts per million. What does it mean is if you take 1 million air molecules, there will be 380 CO2 molecules among in that mix. Okay, and it's already more now because you can see that the table is from 2007, and wow, we already crossed the 400 line. Okay, some years back. So this is a relatively old number here. Okay, and why has it changed? Because humans emit CO2 into the atmosphere. Other greenhouse gases, here is methane. We have methane listed here, and nitrous oxide also listed here. Okay, relatively low contributions, but play an important role in the energy balance in the atmosphere, the heat balance. Ozone is also an important gas because it absorbs solar radiation. Okay, harmful solar radiation. And we talk about particles play a big role. The percentage is very, very low, the particles, but particles can actually form a layer. And the layer of particles can reflect solar radiation. Very, very thin layers, but very effective in reflecting solar radiation. And if you don't know what reflection means, then just wait for part B of this lecture. I think it's in part B. Yeah, it will be explained in part B. CFCs are also listed here in this table because CFCs have led to the destruction of some parts of the ozone layer, which has pretty much recovered in recent decades. Okay, more about the atmosphere. First thing you need to know is what do we mean by air density? The density of air is the weight per unit volume. Okay? You grab 1 cubic meter of air and determine the weight. And the average weight at the surface is around it's around 1.24 kilograms. Okay? And there's a link between air density and air pressure. Okay? Pressure is proportional to the weight of the air column. So if you are at the surface, and this is what's shown here in this graph, it's the pressure. Air pressure is the highest near the surface because the entire air column sits above you. And then pressure decreases because there's less and less mass of air above you, and then reaches very low, almost zero levels at 100 kilometers above ground. Okay, density very similar. Okay, the highest density near the surface. Okay, and then the air gets thinner. There's less and less oxygen in the air, and in fact, about at 8 kilometers above ground, you actually couldn't breathe anymore because there's not enough oxygen anymore. Okay, let's go back one more time. Not finished. At around 8 kilometers above the ground, we have something we call the dead zone. There are also dead zones in the ocean, but they have different, it's also critically low oxygen levels, but in a different context. Okay, in the context of marine life, indeed. Okay, so pressure changes influences and cause phase transitions of water. That's an important link to climate. Okay, because if you lift air masses up, moist air masses up, it can actually induce condensation and cloud formation. Already mentioning this at this point in time. All right, this is about the atmosphere, and we talk about temperature distribution in the atmosphere. We're still not finished with the atmosphere. As density decreases, we again show here the temperature distribution as a function of distance from the sea surface, called altitude. Okay, highest temperature found near the surface, and then as pressure decreases, so does density and temperature. Temperature decreases. Okay, and this is within the layer that we call the troposphere. Okay, the troposphere is the layer that contains the weather patterns. This is the dynamic action happens here. And this temperature decrease with height influences the climate in regions where you have mountains. You can see here Mount Everest, and above a certain height where the temperature drops below zero, you have ice caps. Okay, that's related to that temperature decrease. All right, and the next layer above it is a layer where the temperature is relatively constant, isothermal layer, but then temperature increases again. And it increases because we have ozone in this layer. It's the so-called ozone layer, and ozone absorbs solar radiation from the sun, and creates this heating effect. And then further up, get some temperature decrease again and temperature increase again. But, I will not discuss these other features. So in terms of the climate, the troposphere is the important one because it includes the weather pattern, and greenhouse gases also reach into the stratosphere. The tropopause is the region where we have cloud formation. That's the region where the clouds typically form at around 10 kilometers above the ground. That's fascinating, isn't it? All right. I think that's it, talking about the atmosphere as a first little overview of the key features, okay, and key terms that we will use in the future. And I suggest that you learn these terms. So we talk about the ocean. Okay, the ocean, part of the hydrosphere. Okay, the water system. Let's look at the composition of the ocean. It's shown in this table. Largest contribution, oxygen, 85%, then hydrogen, around 11%. Okay. That's fresh water. Okay, fresh water makes most of makes the most contribution to seawater. 96.5% of seawater is fresh water. Then we have salts. Okay, salt concentration. Mostly sodium chloride makes 35 grams per kilogram on average. Okay, this is what we call salinity, the salt concentration. And the salinity plays an extremely important part in the ocean. Okay, because it influences the density of seawater. We also have an air-sea gas exchange. Okay, the air exchanges gases with the atmosphere, oxygen and CO2. You know that oxygen is also produced in the upper layers of the oceans through photosynthesis, where plankton is formed and also creates oxygen. And so oxygen can actually be outgassed into the atmosphere. And similarly, the ocean actually turns out that the ocean is a major sink of CO2 currently. Okay, it has taken up around 30% of human CO2 emissions have ended up in the ocean. All right, good. Next bit is, well, let's look at bathymetry. What's the typical depth distributions in the ocean? That's what we call bathymetry. And you can see on average here in this map, shows you the colors, and red exceeds 5,000 meters. Okay, and so the average depth of the oceans is actually 3.8 kilometers. That's what we're talking about. And we have three oceans: the Indian Ocean, the Pacific Ocean, and the Atlantic Ocean. And they're sort of confined by continents on the western and eastern side. Indian Ocean also on the northern side. That's what determines the extent of these oceans. And in addition to that, we have the Arctic Ocean in the north, which is a continent-free region, okay, in the northern polar regions. And we have the Southern Ocean. The Southern Ocean is a continuous region around Antarctica, which connects all three oceans. That's what we call the Southern Ocean. There's also continental shelves. Continental shelves are regions which are around 200 meters deep along continents. You can see that the width varies here. It's these areas here which are shown by the bluish colors here around. And these are important because that's where most of the plankton forms in the ocean, you know, in these continental shelf regions. All right, density. Going back to density. So how does the structure of the ocean look like? In just the very, very first description. Seawater density, it's the weight of seawater per unit volume, how heavy water is. Okay. And what you find in the oceans is, anywhere in the ocean, is that the lightest water is near the surface and the heaviest water is near the bottom. Okay. However, the density of water is controlled by temperature and salinity. In some regions, temperature is more dominant, has a more dominant effect. And this actually creates that the warmest water in equatorial tropical regions sits near the surface. Again, this is shown in this figure here. So what's shown here is a horizontal cut from the South Pole to the North Pole across the Atlantic Ocean. You can see the equator is 0. And this is temperature, okay, in degrees Celsius. You can see all the blue stuff, it's cold. You know, lower than 75% is lower than 5 degrees Celsius. It's very, very cold. But you can see this warm lit in red and orange and yellow. This is the warm lit, and it exists because the temperature effect exceeds the salinity effect in these areas, and it's the heating through heat fluxes, the warming of this area that creates this structure. It's totally different in polar regions and cold water regions. In cold water regions, it's the salinity effect that determines density. And it is the melting of ice that creates a low salinity surface water that can be cooled down to the freezing point temperature. You can only form ice if the temperature drops in seawater below 2 degrees Celsius, minus 2 degrees Celsius. If it drops below minus 2 degrees Celsius, sea ice starts to form. This is only possible if you have low salinity water there in the first instance. And the other feature that makes this possible, and it's quite unusual, is actually that the solid form of water ice has a lower density and floats. Okay, so that's the first important hints on what controls the structure of the ocean, and some links to the climate, because you will learn that white surfaces reflect solar radiation and induce a cooling effect in regions. Okay, because of that reflection. Okay, cryosphere. We're talking at last about the ice system. Okay, and we have sea ice. Sea ice is ice that's formed in the ocean. Okay, in this map, you can see the Arctic Ocean. The North Pole is featured here by this dot. This is the North Pole. And without the ice, this would be open ocean. There is no continent or so. This one is just, you know, open ocean covered by ice. Okay, sea ice. Okay, we have ice on snow, snow and ice on land. All right. And on continents we have ice sheets, large ice sheets of Greenland and Antarctica that contain about 99% of the fresh water on Earth. We have ice shelves, and these are floating extensions of ice sheets. Okay, they can also melt in the ocean, like sea ice can melt. And ice sheets can melt if they come into contact with relatively warm seawater. Okay. We have ice in mountain glaciers, ice caps. Okay. And then we have ice in frozen ground, either year-round frozen ground, which is called permafrost, or we have ice in seasonal frozen ground. Okay, and the ice system is very, very important because it influences, modifies the reflection of solar radiation. It reflects. Okay, let's go to the next part of this lecture.